Hey, good afternoon, everyone, and thanks for coming. This is our last lecture of this semester. So, because we have finished the discussion of all the topics we want to discuss, so today we're not gonna talk about anything new. I'm gonna use about like 15 to 20 minutes to do this retrospect, like to briefly thread out what we have discussed and to kind of like strengthen our overall image of this probabilistic learning topic. Hopefully it can make you feel more organized, right? And then after that, we come to the stage of discussion phase, meaning that you can choose to stay here, ask any kind of question you like, or you can feel free to leave for whatever place you want. Okay, so it's completely a volunteer. Like if you can ask questions, you can ask questions about homeworks, assignments, or you can ask whatever other questions. It's not restricted. But if all of you will be gone, then I will be gone as well. Yeah, okay. Oh, by the way, I'm to emphasize the remaining stuff for this class, homework 5, and the final project report. And please do take advantage of the office hours. We still have office hours this week, but next week we won't have any office hour. The office hour will end next week. So if you feel any problem, like you want our TA or me to help, please I feel free to stop by the office hour. Okay. Okay, so let us do a quick retrospect of what of this whole semester, right? To give a very quick summary, right? We can use this figure to show what we have discussed throughout the semester. So, so basically, we have talked about 3 components in the probabilistic learning and their interactions. So at the beginning, we introduced many foundational knowledge, right? That's not very interesting, but we have to know them before we talk about probabilistic learning. So those foundational knowledge, including a variety of probability distributions, right? The basic concepts about random variables, probability densities, expectations, variance, maximum likelihood estimation principle, type 2 MLE, conjugate and unconjugate likelihood, a prior, uninformative prior, exponential family, what are their properties, exchangeability, and so on, right? Those are all like fundamental concepts in Bayesian statistics, which are widely used in practical probabilistic modeling and learning. And once we have this foundation knowledge ready, then we talked about how we formulate probabilistic models. And then based upon the models and the data, how we conduct computation. And so actually, the discipline of probabilistic machine learning consists of 2 components. One is model, one is computation. Okay? So in the modeling, we introduced several general frameworks. Right? The first one, and similarly, the most straightforward one is the generalized linear models, right? So, but generalized linear models are quite flexible because we're assuming that, okay, you have some basis functions or some feature mapping. You can do some nonlinear transformation of our original data. Then you do some linear combination of those basis functions to make prediction. So although there's some kind of linear structure inside a model, that doesn't necessarily mean your model is really linear to the input. It can be highly nonlinear. Okay? And for the neural networks, you can always will them as a generalized linear models, right? Because the last layer is just linear combination of the all bases generated from the second last layer. Right? So, so the second general framework we talk about is graphic models. So as the name suggested, graphic models means that I'm going to use graph and graph theories to describe my probabilistic models. So the graphing model is very intuitive, and you can use that to model any kinds of like conditional independence, right? So remember, how does graph conversal properties connect to the conditional independence? Right? We have baseball algorithm, right? We can with that we can efficiently check any two sets of random variables that are conditionally independent on the third set of random variables. And through graphing models, so we can conduct all kinds of like computation, like message passing. Right? If the graph is a tree, or is tree structured, then we can compute exact marginal posterior distribution for every node in the graph. Right? However, when a graph has loops, right, and there's no guarantee of that, but you can still apply the so-called message passing algorithm or sum product or max product algorithm to get some kind of approximation, right? But that approximation is not exact, although in practice, in many applications, such approximation is enough good, right? Practical usage. Okay, these are two general framework for probabilistic modeling: general linear models and graphing models. And then we'll talk about two more specific probabilistic models. One is called Bayesian neural network. The other is called Gaussian process. Right? So Bayesian neural network is based upon like the hot neural network topic, right? So if you want to enable some uncertain quantification and posterior inference in neural networks, the most straightforward way is that you're gonna treat the random variables, treat each neuron in the neural networks as a random variable. You can assign some prior distribution, right? For example, a standard Gaussian prior distribution or some mixture prior distribution, whatever you want. And then your output of neural network obviously will become another random variable because it's a function of all those neurons that influence, right? So then you can develop methods to estimate the posterior distributions of these neurons given the training data, right? And then we'll talk about how to do this efficiently, right? With using the variational inference framework, right? That relates to computation, right? And then we'll also talk about Gaussian process, although we only have one lecture. Talk about Gaussian process, but we did cover the fundamental idea of Gaussian process. So it has a very beautiful, elegant theory on that. Like I can create a prior over functions through the random processes, because the random processes are theories about function priors. How do you assign or map random experimental outcomes to function curves? Okay. So, and the Gaussian process is one of the most popular functional priors. And then we'll talk about how do we project the Gaussian process prior into finite set of data, which actually is reduced to a multivariate Gaussian distribution, right? And then given the data points, you can do the posterior distribution, you can do the prediction. They are all based on the conditional Gaussian distribution. Right? So it's fairly convenient. And then we have so many models, right? They're powerful. They're diverse, right? They have you can use them to model a variety of different data and phenomena, right? And then the other task is that, okay, we must be able to compute something we're interested in, right? We must be able to compute our prediction. We must be able to estimate the distribution of some unknown parameters or the prediction. So that relates to the second topic. Another topic in probabilistic learning is computation. This is actually equally important to model, right? Because if you only have a model, you don't know how to compute, then your model is useless. Right? You must know how to efficiently compute that. Right? So we'll talk about several, like briefly, 3 types of inference algorithm. Right? In addition to exact inference algorithm. That is the sum product or max product on tree structure graphs, right? That was covered when we talk about the graphic model, right? But we'll deal with like general probabilistic models, right? Usually you won't be able to compute exact posterior distribution. You won't be able to so you have to seek for some kind of approximations. So we introduced the Laplace approximation, variational inference framework, Markov chain Monte Carlo sampling framework. And Laplace approximation is perhaps the most straightforward approach. So its basic idea is, okay, I'm gonna use Taylor expansion. I expand my log joint probability at the map estimate. I use my second order Taylor expansion, then I can construct some multivariate Gaussian approximation to the posterior, where the mean is your map estimate, and your covariance matrix is the negative inverse of negative Hessian. And if you still have some kind of impression of that, it's fairly straightforward. And then we talk about a variational inference framework. Right? The variational inference framework essentially is trying to use a simplified form to approximate a super complicated posterior distribution. Okay? So suppose this is your true posterior, which you don't know the form, which you know it is infeasible to get the form. So my strategy is that, okay, I'm gonna introduce a set of approximation, a family of approximation like Gaussian or mixture Gaussian, or student whatever you like. And then we want to, from this family of approximations, find out the best one to approximate the true posterior. So the best means that there's some kind of measurement between the true posterior and the approximation to be as close as possible. So in the variational inference framework, the most commonly used measurement is called KL divergence. You want to minimize the KL divergence between your approximation and the true posterior distribution, right? That's the basic idea. However, you are not able to directly minimize the KL divergence, so we have to do this indirectly. How can we do that? We maximize the so-called variational evidence lower bound. As long as you can compute or optimize an expectation of logarithm of the joint probability divided by the approximation, right? As long as you can maximize this guy, it is equivalent to minimize this KL divergence. So we discussed why. Right? This is just the application of Jensen's inequality. And then based on this framework, we're talking about several different approaches, right? Like the global variational inference, where you can just parameterize your Q theta as whatever form you like mean field approximation or Gaussian, whatever, right? And the local variational inference, where you further apply some inequalities or convex conjugate, something like that, to kind of a lower bound some term in the joint probability to make the form, make the evidence lower bound even easier to compute. That's called local variational inference. And the third method is that if it is really difficult to compute, right? Meaning I even do not know the exact form, because sometimes even your Q theta is simple. This whole log fractional might still not be analytically tractable, like Bayesian neural network. Right? You can assume, okay, your neurons, the posterior of neurons are Gaussian, right? But you cannot compute the expectation of your log neural network likelihood of a neural network output. Why? Because your output is a highly nonlinear function of those neurons. Even you take expectation with respect to some Gaussian, it won't give you some closed form. So in that case, you can use the so-called reparameterization trick. Right? You can use the cluster optimization. Right? So you want to generate some stochastic sample of your parameters, and then you plug it into this log fractional and compute the gradient, which we call the unbiased stochastic estimate of the gradient. Right? This is called stochastic gradient, so you can use stochastic gradient descent to optimize this evidence lower bound. But the problem is that you have to ensure that the expectation under which the distribution under which you take expectation is not dependent on the random variables, the parameters you want to optimize. So you have to use the reparameterization trick. Okay. So if your Q theta is a Gaussian distribution, right? You can try to represent theta as mu plus some square root of the variance times some standard Gaussian random variable. Right? In this case, you kind of like decouple the random variable and the variational parameters you want to estimate. The expectation now becomes the expectation under the standard Gaussian random variable, the standard Gaussian noise. In this way, your stochastic optimization will be a lot easier. So that's the basic idea, and this is very, very popular because in practice, especially if you involve neural networks, this evidence law bound won't be able to won't have any closed form, right? And you're doing reparameterization trick and the stochastic optimization, that would be the most convenient way. Oh, by the way, you guys can interrupt me anytime. I'm just I'm not gonna go through every detail. I just want to like refresh our mind for those like ideas. Okay. And then we'll talk about a third branch of computational technique. It's called Markov chain Monte Carlo sampling. Right? So it uses a fairly different idea. Right? It kind of simulates a Markov chain, and if your chain is constructed properly, it can guarantee that your samples generated by this chain will asymptotically respect the target posterior distribution. Right? So the key is to construct a Markov chain. Right? Of course, the chain construction is related to the joint distribution of your model. Right? So we talk about the detail balance, right? And to ensure detail balance is guaranteed, your chain will converge to your target distribution, right? And so that when we want to design your chain, namely, how do we design a conditional distribution or transition kernel, you have to make your transition kernel to satisfy detail balance so that to ensure your target distribution is invariant to your chain, and also other stuff. Right? We'll talk about the easiest Markov chain Monte Carlo algorithm is called entropy listing. Okay? And you can use constraint Gaussian to sample the proposals. And that's really bad because it will give you random walk behavior. It doesn't know any information about your distribution, so just blindly generate samples, and it's very likely to be rejected. That's called random walk. And then people develop a so-called Gibbs sampling. Right? Their transition kernel is just a conditional distribution. Right? And Gibbs sampling ensures that acceptance rate is always 1, but it's limited by the strong correlations between the random variables. So it cannot efficiently explore the whole sample space. Then we'll talk about Hamiltonian Monte Carlo sampling. It uses physics systems called Hamiltonian system to simulate a trajectory of samples, right? So because of some nice properties of this Hamiltonian system, you can guarantee that, okay, you can evolve for quite a long trajectory, but still preserve a high acceptance rate. So kind of overcome both the issues of both the issues of random walk and also the strong correlations between the latent random variables. Right. So that's all like kind of like for what you can discuss throughout the computation. And actually nowadays the techniques, the advancement of computational technique in probabilistic machine learning is still within this framework, either variational inference or Markov chain Monte Carlo sampling. For example, a few years ago, like there's a hot topic is doing like stochastic Monte Carlo sampling. Okay? Stochastic Monte Carlo sampling is kind of like throughout the acceptance test, because when you do the acceptance test, you always need to compute some like log joint probability over the current samples and divided by log joint probability over the previous sample. Right? That means you have to go through all the data. That won't be good. That won't be efficient for large data. So people are trying to get rid of this so that you can largely accelerate the speed, but the price is that your chain won't guarantee to converge the true state. Okay. Or their statement becomes some kind of like probability statement, like with large probability to converge. Okay. So okay, so here we just use like about 10 minutes to walk through all we have discussed throughout this semester. And we believe that our course covers enough topic, but definitely not in depth. Actually, any topic in the modeling or in the competition can have a large number of literature. Okay? Like Markov chain monocount sampling, like we look at the literature, there's huge amount of papers about that. Okay? Like variational inference in 2008, Martin Wainwright and Michael Jordan has written a book, like I think it's 3,000 pages about graphic models, exponential family, and their connections, and all kinds of stuff. If you really want to go deep about graphic models, that's really a good book. It contains everything you want to know. But I hope this whole framework and this structure can give us a kind of like a good organization, so that in the future, if you want to go deep for whatever subtopic, you will not get lost, because there's so much content in this area. Okay, so going back to a more general concept, what is probabilistic or Bayesian learning? So in a nutshell, probabilistic learning is a branch of machine learning that uses probabilistic principles or Bayesian principles for the model design and for the algorithm development. For the model design, meaning that, okay, your formulation, the learning objective should have some probabilistic interpretation. Second, your algorithm development means that, okay, if you're only doing point estimation, that's not good. We always want some kind of uncertain quantification. Right? Ideally, we want to deal with it in a Bayesian way, meaning that I can quantify the posterior distribution of anything I'm interested in. Right? That's the principle or method of probabilistic learning. So probabilistic learning is like is very like how human beings are learning, right? So before we learn something, we always have some prior beliefs, prior knowledge encoded in our brain. And when we say something, when we read the books, when we watch the videos, see whatever data from the computer, it is always real data, right? So we got some data likelihood to encode information data, and then we kind of like integrate our prior knowledge and the data likelihood to update our knowledge, right? The updated knowledge is described in the Bayesian word as posterior distribution. Right? So, and the golden standard to integrate your prior beliefs and your data information is through the so-called Bayes rule. And I call it golden standard means that it is good, but it's really not achievable, right? Because of this computational bottleneck, right? The denominator, which is a integral of the prior and likelihood, is really infeasible. Right? So I have to seek for efficient approximate computation, right? So there are a variety of advantages of using a probabilistic framework for the modeling, right? So it gives a unified principle mathematical framework to encode our prior knowledge and integrate with data, right? And it also allows us to reason under uncertainty, right? Because ideally we want any probabilistic learning system will give you a posterior distribution, right? Not only the points estimation, so that means you have more information. With this more information, you can make decisions for the subsequent tasks like autonomous driving or climbing, whatever. And that will usually give you a better outcome. Right? So, but there are also challenges, right? For the modeling, we know probabilistic learning or probabilistic models always require that beliefs will be included as distribution. But for many structured knowledge, like graphs, like hierarchies, like rules, how can you convert them into distributions? That's something we need to think about, because in human world, right, we won't always think about what is the chance of this rule works, what that chance works. Right? We say, well, rule number 1, 2, 3, 4, just apply. But now, if you want to convert them into a valid prior distribution, how can we do that? Right? And second thing is computation. As we mentioned, if you want to compute the posterior distribution, in 99.5 cases, you won't be able to apply Bayes rule. You have to seek for several approximate computation technique. Right? And although we have like several frameworks, right, frameworks for computation, but it's still not sufficient. Like, for example, in the variational inference, like in our discussion in the class, we pre-assume your posterior distribution has some form like Gaussian. But the cutting edge research about variational inference is not like that. They use a so-called normalization flow, a gradient flow, to do that. Why? Because they don't want you to your Q theta, your approximation, to be restricted to a particular family of distributions. They want the user even not be aware what kind of approximation they got. How can we do that? They just keep doing some kind of transformation of the variables. At the beginning, you can imagine, okay, you use some Gaussian to approximate that. But I can apply a series of steps of transformation. When you have some Gaussian random variables, you take square, it won't be Gaussian random variables anymore. Okay? When you take tan H or that, it will be more complex. So imagine like you got a series of transformation, nonlinear transformation of random variables, and you can update the transformation parameters in the variational inference framework. You can imagine, well, the real family of your approximate distributions can be really large, right? You actually don't know. This is called normalization flow. Right? It's pretty popular in the variational autoencoder and also some recurrent neural networks if you want to do the inference. Okay. Foundations of Bayesian learning. Probabilistic space, random variables, cumulative density functions, PDF, marginal conditional distribution, and so on, and convex function, convex conjugate. Those are all things we have gone through. But again, sometimes you won't be able to memorize them all the time. Like sometimes you have to go back to look at the book from time to time. Right? But just keep in mind, those are important. Right? Commonly used distributions, Gaussian, student T, Bernoulli, multinomial, Dirichlet, softmax, and so on. Maximum likelihood estimation principle, map estimation, type 2, maximum likelihood estimation, empirical base, conjugate prior, gamma Wishart prior, exponential family, Bayesian decision theorem, optimal decision, and so on. Uniformity prior, Jeffreys prior, exchangeability, definitive theory, and so on. Right? Again, we're not able to cover every detail about every concept here, but hopefully we have given you a good introduction to them. Right? In the future, if you want some more in-depth discussion, you can just search for the literature. Right? And modeling, we have talked about a variety of families. I'm not gonna go through this again, right? Okay, so when you practically, right, when you want to design some probabilistic model, like what kind of problems, what kind of things you should be aware of? So you should first figure out what is the key assumption of the model. That determines what type of models you want to use. Like you want to use linear regression, you think that is enough, or logistic regression. Right? So that means your underlying assumption that, okay, linear relationship between the input and output you believe is sufficient. Right? Or you want to use neural network, right? You want to use one layer neural network or use 100 layer neural network, right? So that actually the choice depends on your practice, but also depends on your domain and what kind of likelihood do you want to use, right? So you want to use conjugate prior, or you want to use more complex prior, like mixture of Gaussian or half Cauchy distribution, all kind of stuff, right? So, and why do you use those kind of prior, right? If you want to learn some sparse signal, right? You want to extract some sparsity knowledge, you might use some sparse inducing prior, like Laplace prior or spike and slide prior, right? And what kind of likelihood, right? What kind of likelihood do you believe is most appropriate to describe data, right? For example, for continuous data, people might by default use Gaussian likelihood, right? But this is actually not very good. Right? In many cases, like when the data has a lot of noises or the noises are not simply a Gaussian noise, Gaussian likelihood is not good, right? You might consider other likelihood like T likelihood, like student T likelihood, or you can consider some non-stationary likelihood where your noise can change along with the input location as well. Right? Third problem, right? What is the joint probability? Right? So when you conduct Markov-Chain Monte Carlo sampling or variation inference, to make sure your implementation is right, please first write down the joint probability. Right? If you cannot write down the joint probability, there must be something wrong in your model design. Okay. And fourth one, right, should consider what's the connection and difference between other models. What kind of other models you want to use, right? And if you're not satisfied with that models and you propose a new one, then what's their connection? Right? What's the key difference? Right? What's your advantage? And computation is essentially to in twofold, right? The goal is twofold. First, this is our parameters data, right? We want to estimate the posterior distribution of our parameters of interest given the data. You can use whatever approximate technique you want, right? And then given this posterior distribution, we want to compute the predicted distribution. Predicted distribution means that, okay, given the training data, right, given the test input, what is the distribution of the test output, right? So that's the good thing about the Bayesian or probability learning, where you can marginalize out all the possible parameters according to their posterior distribution. In this way, you ought to get better, more robust prediction performance. And again, this integral is really not analytical, right? You have to use some kind of approximation. The most commonly used approach is that, okay, you do some sampling from your posterior estimation of the data and then do the Monte Carlo approximation, this guy. And here are the efficient Bayesian inference framework. We talk about the Laplace approximation. Oh, by the way, EML algorithm, we missed it when we talk about the variation inference, right? But EML algorithm is a good introductory step to the variation inference framework. And Monte Carlo and Markov-Chain Monte Carlo sample. Right? And for some specific models, like you might still apply some simpler inference algorithm, like for Gaussian mixture model, you can just apply EM algorithm. There's no need for approximation because given the data, you are able to compute the posterior distribution of the cluster memberships and cluster their cluster memberships or cluster indicators. But for many other models, like even given the data and given the parameters of interest, you are not able to compute the posterior of the random variables. You have to seek for the approximate inference. Right? So we'll give some example for the latent Dirichlet allocation. Right? This is essentially a variation EM algorithm. Right? And we'll talk about Bayes by backpropagation for Bayesian neural networks, and we'll talk about the variation inference for autoencoders. So those are like typical examples for the inference of probabilistic models. They're not only like just pedagogical, they're also very useful. They're used everywhere. So we hope that you should have some like good impression about those algorithms, right? Because they can be used as some kind of reference when you develop the inference algorithm for your own models. when you develop your own model inference algorithm, again, you should first figure out what is the key idea and assumption about algorithm, like that make you decide which type of approximate inference algorithm you want to use, Laplace approximation, variation inference, message passing, or the Markov chain Monte Carlo sampling, right? And then you can choose which framework, right? And and you also need to inspect or verify why you're making such kind of assumptions are reasonable, right? Because you're doing some approximate inference, and you always need to make some sacrifice, some kind of accuracy. I need to figure out why your sacrifice is good, right? or is acceptable. This can either done by your domain knowledge or through your trial, like trial and error cycles, right? And also you need to be aware of the computational cost. And in general, people will believe that Markov chain Monte Carlo sampling is much slower than variation inference on all the other type of methods, right? But in some cases, it won't always be like that. So, for example, in 2018, David Danson, who should be the most top, like toppest scholar in Bayesian inference, Bayesian statistics, he claimed that actually most people do not know the right way to run Markov chain Monte Carlo sampling. If you know the right way to run it, it is also very fast and can scale to very large data. Okay. So this is just an example to show that in practice you should be aware of the computational cost, and those are important placement for you to choose the algorithm you want to use. Okay, to summarize, probabilistic learning is a huge branch of machine learning, right? And due to time limits, we can only introduce the most important concepts and ideas, right? And it's promising in modeling, yet challenging in computation, right? It is an elegant marriage of math and engineering. That's why I'm always fascinated in this area, okay? And it's hot in research and has a growing attention in industry. Why the growing attention in industry? Because industry does need some uncertain quantification, right? So I take some recommendation task as an example, right? So if we want to recommend something, it's not like, okay, just throw out an item to you. So they want to predict the likelihood you're going to like this one, right? And then you're going to look at the confidence of your prediction, of your model's prediction. If your confidence is super high, then no problem. I just recommend this item to you. However, if your confidence is not that high, right, then they're gonna do some kind of trade-off. For example, if your confidence that the customer likes this product is only 60%, then we'll think like, why not just throw out some completely new thing to the customer and to give there some freshmen. That's very important. Otherwise, if you keep recommending the customer the same thing, the same type of thing, they will soon go forward. So to make such kind of trade-off, they also call it exploration and exploitation trade-off. You have to have some kind of uncertain quantification, right? And in industry, people wouldn't do that in some principle way. They just come out with some kind of uncertain score, just rank the score. Okay? But if you can do the Bayesian inference, probabilistic inference, like highly efficiently and principally, the industry will love it. Another example is called Bayes optimization, right? If you want to optimize some black box function, you don't know the form, you don't know the gradient, you want to evaluate, right? A typical approach is to use Gaussian process or student T process to model that kind of function. And then they're gonna, according to the points at which you have a probe the function, right? They can decide, okay, it looks like they should be in between those create functions, right? That is function values. That is based upon what you have this probed so far. But you would also like to probe new places, which is far away from the places you have a probe. This is also called exploration and exploitation trade-off. And you can always explore. That will make you cost a lot of time to find the function maximum. But if you just explore, just exploit, meaning that, okay, just look up like the past function values I create, I just pick up the largest one. That will make you stuck in some bad local optimum, right? So it's always like such kind of trade-off. And again, you need some good uncertainty quantification. Right? That's why in Bayesian optimization, Gaussian process is very popular because the uncertainty quantification about Gaussian process is just the condition Gaussian. It's very easy to compute. And although there are some computational challenge in Bayesian learning or probabilistic learning, more and more general libraries are developed for convenient usage. Like you can search for, like there's a package called GPY Torch, right? Is a Gaussian process library, general Gaussian process library, for based upon PyTorch framework. And it's very easy to use. Right? There's also some, I kind of forgot. It's called a probabilistic programming library. Like you can choose, you can construct whatever distribution you like, and you can choose a variety of Markov chain Monte Carlo sampling algorithm to inference that. Okay, I forgot, but it's a very convenient and powerful library. I used them before. It was written based on Theano. How many of you have heard Theano? Oh, good. Yeah, Theano was kind of like, I think, father of TensorFlow, and but it was really efficient. Very hard to debug. That library is based upon Theano. Okay, so again, thanks for your joining of this class, and I know that this class is pretty challenging. We'll spend a lot of your time, and happy that all of you stick to this class and doing great. So I wish you a great success in the future, and I wish that you have discussed and learned from this class will help in whatever aspect in your future. Okay, let's stop here.